Okay, so you got the next web work is due tonight at midnight. We'll do a couple more examples of the undoing the product rule, and then in that web work they're mixed. They're mixed together. So they're not just all undoing the product rule. Okay, there may be some undoing the chain rule there too. So just because, and that's a skill that you have to learn is once we get through all these techniques, coming to a net accumulation function, an open form, an integral, and knowing what technique to use. So the second web work on doing these, called undoing the product rule, it might have some undoing the chain rule in there too. So start learning that. Start learning how to identify, right, what technique you're gonna need. So let's look at so for the undoing the product rule, a real common type of problems are problems that involve natural log of x. For instance, just natural log of x. So thousands of students throughout the ages has said this antiderivative is what? What do they think it is? 1 over x, right? Antiderivative is 1 over x. Is that right? No, that's the derivative, right? That's the derivative. We want the antiderivative. And so we're thinking to ourselves, what function, if we took the derivative of it, it would be natural log of x? Well, there's no elementary rule for that, right? There's no, if you think back on all your rules that you learned in Calc 1, there is no function that if you take the derivative of it, or like a real basic function, that if you take the derivative of it, you get natural log of x. Okay? So we're going to apply undoing the product rule. And so we're going to see this thing as fg prime. But how can we see that as fg prime? No, they're not multiplied, right? That's a function acting on x, right? That's all one thing, a natural log. Yeah. Okay, yeah, so this is often a thing that will, and I think did we see this before with undoing the chain rule? 1 times, we saw it with the exponent, right? We had to see tangent inverse to the first, right? Even though the 1 wasn't there. So here's the same deal. We need to see this as 1 times natural log of x. That's not a 2, that's a 1. Okay, 1 times natural log of x. And so then, remember, we have our choice. So something's going to be f, and something's going to be g prime. And then what are we going to do? We're going to take the derivative of f, because we're going to need f prime, and we're going to need the antiderivative of g prime to get g, right? So let's be a little forward thinking here. Here we need to do the antiderivative, right? So is natural log of x going to be g prime? No. Because what happens? We're going to have to do a mini antiderivative of natural log of x. Well, that's the problem we were given, right? That's the problem we're trying to figure out with the antiderivative of natural log of x. So it doesn't make sense to put natural log here. Because then to do undoing the product rule, we have to solve the problem that we're trying to solve. Does that make sense? So that leaves us with what f is going to be? And g prime? 1. So now f prime. So now what's derivative of natural log? 1 over x. Now, antiderivative of 1. We can do that. X. Now we can do it, right? So we're going to set up our f times g is x ln x equals what we're trying to find, right? Plus, we're going to do the other one, right? The easier one, and that's g f prime. So it's going to be x times 1 over x. And what is that? That's 1. So our answer is x ln x minus Antiderivative of 1 dx. What x? You should be thinking it's x. And then we also need plus c. So x ln of x minus x. So when we say uses the language in the textbook, the principal antiderivative. So the principal antiderivative is the one of these, right? So this is a whole family of antiderivatives. It's all the functions that have ln of x as their rate function, right? Because we know we can start at any value of a, right? We can start accumulating at any value of a. That's what the plus c is for. So the principal antiderivative is the one of these where c is 0. Okay, so the principal antiderivative, if you ever just want to know what the principal antiderivative is, it's just the one where c is 0. So all antiderivatives, you need the plus c, right? Starting from any a value, starting to accumulate from any value a, or little a right there, right? But if you say the principal antiderivative, you just mean, now, does that mean you're starting from 0? It doesn't necessarily mean you're starting from 0. It means f of a is 0, right? It means f of a is 0, because that c is the minus f of a, right? Okay, any questions on that example? Okay, so then we talked about so last time we did this example. And what happened in this one? We set f equal to x squared, right? And g prime was e of x. And then f prime was 2x. And then g was e to the x. And then we got this one here was what then? It was antiderivative of 2x e to the x, right? And so we said, well, we don't, how do we do that? How do we do that one? We did the product rule on that, right? So when we got to this quote-unquote easier integral, well, it was kind of easier because it had 1 degree less than the x squared went to x, but we still need to do undoing the product rule, and then we've got it, right? So we did undoing the product rule like within itself, right? We had a sub-problem that required undoing the product rule amidst the bigger picture when we were doing undoing the product rule. Okay, so what if this was, say, x to the 5th? Then what would you expect? Yeah, you'd have undoing the product rule embedded in the solution 5 times. You'd have to keep like nested. You would keep getting nested within, right? Until this x to the 5th finally got down to 1, x to the 0, right? Every time you do it, you'll take the derivative and bring that power down by 1. And then when finally we get down to x to the 0, then we'd be able to do antiderivative of e to the x, and then we finally have it, but not before, right, doing this 4 times. Okay? So we don't want to do that, right? We don't want to do that. So x squared is good enough. Maybe x cubed. Pay your dues, do it once, be done. But, x squared is good. So this is a common form that we'll see for undoing the product rule, where you'll have, x to the n times like e to the x, or cosine x, sine x. And so what will we do? We're always going to choose f to be which? Is f going to be x to the n, or is f going to be this one of these transcendental functions? X to the n. We're always going to choose the f to be x to the n, and then choose that to be the g prime. And then how many sub-problems will we have to do to solve it? How many times will we have to do it? N times, right? N times we'll have to have undoing the product rule involved within itself to get it right. Okay, any questions on that? Okay, so then what about So what about x to the fifth ln of x? Did you do this one? Was it a reflection question? Okay, so how many times do we have to do it? So first of all, do we let that be f and that be g prime? Is that our assignment? Why not? Why is that not our assignment? Yeah, it's because again, since you have to do this like this antiderivative ln. So instead, so this is a little different than the ones I was just showing you with e to the x or sine x. We're going to do this. So right off the bat, it's different, right? So the reason the other ones took 5 times is because we were letting x to the fifth be f, and we knew that with every derivative, we would reduce the power by 1, and it would take 5 times then to get it down to x to the 0. But so right off the bat, it's different. So is this going to take 5 iterations, or what's going to happen? So why don't you, if you haven't already, but no, everyone go ahead and do it. So you're going to assign x to the fifth to be g prime, ln of x to be f, and see what happens. Go. So you're going to work on this one. No, don't just tell me the answer. Tell me what you did. So we got f is going to be ln of x, right? And g prime is going to be x to the fifth. Okay. So where'd you go from there? Uh-huh. Good. Okay. Are you doing f times g?
Yes.
Yep. F times g, 1/6, x to the 6th, times ln of x. Okay.
And then g prime is x to the fifth ln of x.
What we're going for, right?
And then plus g f prime, so 1/6 x to the 6 times 1 over x.
Okay.
And that equals 1 over 36 times 1 over 36 x to the 6.
So this, you're doing the antiderivative of this?
Yeah.
So it's 1/6 x to the 6th over x is
Oh, okay.
x to the 5th. And now you're doing the antiderivative, so that's where you're getting the 1/36th.
Yeah.
Okay. So we're going to do the answer is, good, so 1/6 x to the 6th ln of x minus, it's supposed to be 1 over 36 x to the 6th. Agree? So look, we had x to the 5th ln of x. How many times did it take? Once. So this is different, right? This is different. We knew it was different from the start because we didn't assign f to be x to the 5th. We assigned the g prime to be x to the 5th and ln x to be f. So that right off the bat, it's different than if it's e to the x or sine x or cosine of the x. And then it turns out you can have any power of x, right? So x to any power times ln of x. I mean, this just shows that you're going to be able to do it just in one step. What is this? Can you describe what this is? So we're getting around with lots of algebra, lots of memorization, lots of rules, lots of methods and procedures, but let's not lose sight of what that is. What is that? What's that? We use the fundamental theorem, but it's not itself the fundamental theorem. What is it? Somebody please know. Yeah, go ahead. What's that? Closed form of what? Okay, and so, but then what is that, right? It's the closed form. What is the integral of x to the fifth ln x dx? That's the open form, right? But of what? So what is all this stuff? What's that? Right. It's a closed form. It's actually it's all right. It's all closed form. Net what? Accumulation functions. Which ones are they? Which accumulation functions are they? Megan, you said it. Which functions? Which ones are they? That have a rate of change of x to the fifth ln x. That's what that is. That's all closed form net accumulation functions for a quantity whose rate of change is x to the fifth ln x. And what do we mean by when we say all closed form net accumulation functions? Isn't it just one net accumulation function? What do we mean by all? Harrison, what were we saying? Right. So the plus c means that net accumulation starting at any x value a, right? Starting at any x value a. As soon as we pick a particular a, then we have a particular value of the constant plus c. There's minus f of a, right? Minus f of a. And then we'd have one net accumulation function, a particular net accumulation function, starting from some a that has that rate, x to the fifth ln x. Okay, so don't lose sight. We're getting into all this algebra and, follow the rules. But the most important thing is what we're finding a closed form version of the net accumulation function for that rate of change, x to the fifth ln x. Okay, so let's kind of summarize the common forms here. So undoing the product rule, there's some common forms, the ones we've seen before, and then these are your tip-off that you're going to use this technique. Okay, first one is some power of x times sine of kx, so it's k some constant. All right, and then how many times of undoing the product rule will it take to get this? N times, right? N times. Same thing, and then so this could be cosine x too. Maybe that's not sine or cosine. Okay, same thing here. Same idea, right? X to the n e to the kx. Okay, again, it takes n times, n iterations of undoing the product rule to solve it. Okay, natural log of x is we just solved that one. And then we said one of these, right? X to the n ln of kx. How many times did it take to find this closed form antiderivative? N times, right? N times. Right? How many times? Once. It only takes once, right? We just did x to the fifth ln of x. It can be x to the thousandth, right? If it's x to the thousandth, it just only takes one time. Okay, so then other common forms are, which aren't on this list, are inverse trig functions. That's when the rate, right? So the rate is an inverse trig function. If the rate is an inverse trig function, this also calls for undoing the product rule. So you're going to work on, take about 5 minutes and see if you can do. Find a closed form net accumulation function for tangent inverse. Find a closed form net accumulation function for this open form net accumulation function. Did you get started on this? Tell me. He wants f to be tangent inverse, g prime to be 1. Is that right? Yeah, that's the only thing we can do, right? If we make tangent inverse g prime, then we got the situation where we have to get the antiderivative, we have to get g. Well, that's the problem we're asked to do, right? That's the problem we're asked to do. Okay, so keep going. F prime is? Good. All right, and then we got fg equals answer minus integral g f prime. So answer is f times g is? Good. Now that's supposed to be easier, right? That one's supposed to be doable, easier. Is it? Okay. So we look at that and we say, if we started right and we're able to keep going, we got to do that. Angel, what do you think?
Well, we have to do the, I don't know, this is the extent where I got.
Okay, cool.
But, we gotta do it, again, we have to do the product again.
Nope. Yeah, Shane.
You could take the antiderivative of that.
How?
So it gives you ln of x squared plus 1 over 2.
And what are you doing to do that? Do you know? What technique is that? Yeah, that's right. This is undoing chain rule, right? Why? So do you see the condition is met? Here's our f. Does that qualify for f prime? Is it the right thing to be f prime? Yes, it's got the right power, right? This is x squared, that's x to the first. And that's the only way it would work, right? If this power is 1 less than that. And it is. So it's undoing the chain rule. Remember, so undoing the chain rule is like it's the most prevalent, the most important one. You're always on the lookout for it. You always, when you come to a problem, kind of ask, that's always the first one you ask about too. You always say, is it undoing the chain rule? And if it's not, then you move on to another technique. But then we see it comes into, you'll see it in combination with other techniques, just like this, right? All right, so who was telling me what this was? Forgot. Oh, Shane.
ln of x squared plus 1.
Okay. What's that?
Over
1/2. All right, so we're going to do the antiderivative of g prime, right, which is this to the minus 1, which is natural log, right? That's the one exponent where it's different. Any other exponent, you undo the power rule, but exponent of minus 1 is natural log. And then we need the 1/2 because of the x squared, right? We think about taking the derivative of that. We're going to have, in the chain rule, we're going to have times 2x, a 2 that we don't have here. We need the 1/2. Okay, so we said that you should do absolute value. Here it's not necessary because x squared plus 1 is always positive. But you can always put it on there. It doesn't hurt to put it on there. But here it's okay to leave it off. So either way. And then plus c. Questions on this example? Okay, tell the person next to you what the profound, deep meaning of that is. Go, tell the person next to you. What is that? What is that? Okay. What did you say? McKenna, what did you say? Morgan. Yeah, good. So all closed form net accumulation functions for a quantity whose rate is tangent inverse x, right? So it's all closed form net accumulation functions of a quantity whose rate of change is tangent inverse x. Okay, so that's undoing the product rule. Like I said, you have more practice if you haven't finished the web work. And then be on the lookout for undoing the chain rule mixed in there too, okay? Any questions about the first two techniques? Okay, so let's start the next one. We'll introduce the next thing here. Last chance. Any questions? Okay, so the next thing is find the antiderivative if the rate of change function is a rational function. What's that? A rational function has the form capital R for rational function. A rational function is this, where n and d are polynomials. So when you put one polynomial divided by another, you get what's called a rational function. Okay, a rational function. So we've already seen some like that, like the one we just did, right? We just did this one. That's a rational function. But this rational function qualifies for undoing the chain rule. So we use undoing the chain rule, okay? Always ask that question first. So some rational functions might be undoing the chain rule. So be on the lookout for that. Okay, what about this one? That's a rational function. So first question we ask is can you do undoing the chain rule on that? Okay, what small change could you make to that so it would be undoing the chain rule? What's the smallest change you can make to that so that undoing the chain rule would apply? Kinsey. She wants x cubed in the denominator. What do you think? Is that right? And then your first attempt would be? What would the first attempt be? We've got x cubed plus 1, and this is essentially to the minus 1, right? So what would it be? Natural log, right? Natural log of x cubed plus 1 would be your first attempt. And then we'd have to work out the factors. We'd have a factor of 3. We got this 2 up there. So we got some stuff going on there. We'd have to clean up the mess, right? But our general form of it will be natural log of x cubed plus 1. Absolute value. Okay? But it's not, we don't have an x cubed. So this is the one we're doing. So it's not undoing the chain rule. It's not undoing the chain rule. So here's the first thing with these rational functions. If n is greater than or equal to, the degree of n is greater than or equal to the degree of d, then we're going to begin by doing long division. Okay? So we got to review long division of polynomials. So does this one qualify? Yes. The degree of the numerator is 2. The degree of the denominator is 1. And even if they're equal. So if the degree of the numerator is greater than or equal to, we're going to start with long division. So that's what we got here. So let's do it. So how does this work? We're going to do x plus 1. All right, and so then when you write this when you write these polynomials in here, you have to leave columns for everything. So even if there's no linear term, you want to do 0x. If there's no constant, plus 0. Same with over here. So make sure you get every power of x, even if it means having 0 coefficients. Does that make sense? So remember what we're doing here? So we're saying what times x plus 1 is going to give us the term 2x squared. So it goes away, right? This is long division. So what do I need to multiply by x plus 1 to get 2x squared? 2x. And that 2x is going to go in the x column. So I get 2x times x is my 2x squared. And then 2x times 1 is 2x. And then what do? Subtract. Remember your long division? We're going to subtract that whole thing. And there's the 0 that I wanted, right? That's why I picked 2x. So when I subtracted, I would get 0 there. And what's my other term? Minus 2x. Okay, so now I ask, what do I multiply x by to get minus 2x? Negative 2. So I'm going to go minus 2. And so we get minus 2 times x is minus 2x minus 2. And I'm going to subtract, right? I'm going to subtract. And if I did this right, that'll be 0. That's what I wanted. That's why I picked minus 2. So that when I subtract, I get 0. And then minus 2, this is going to be plus 2, right? Minus a negative 2, that's plus 2. So now we're done with our columns. So the quotient, so this 2x squared over x plus 1 equals the quotient plus the remainder over the divisor, right? So it's going to be my 2x minus 2 plus the remainder divided by the divisor. So for a lot of you, that might have been a long time ago, if ever. But you do the same thing that you do just long dividing values, right? It's the same kind of thing. Anybody have a question on what I did? I'm sure that many of you have not done that in a long time, if ever. So do you follow what I did? You can ask. It's okay. So now if those two are equal, then we can, so this is the rate function, then this is also the rate function. So this antiderivative is the same as the antiderivative of this, right? Which is, we're becoming experts at antiderivatives. This is an easy one, right? Let's just, I'm not going to write it out, but so the antiderivative will be of each one. Antiderivative of 2x is x squared. Antiderivative of minus 2, minus 2x. I'll write it out, it's easy. So x squared minus 2x. Antiderivative of 2 over x plus 1. Is there a plus? That's a plus. Thank you. It's a plus. Okay, plus 2 ln of absolute value x plus 1, because all that is x plus 1 to the minus 1, right? Plus c. All closed form net accumulation functions of a quantity whose rate of change is 2x squared over x plus 1. Okay, so sometimes this fraction will not be simple, but you'll get a new rational function where n is less than d. Okay, so that's what's going to happen when you do the long division. You'll get a new rational function where n is less than d. In this case, it was easy. It was just natural log. But in other cases, it might not be easy, and that's the next technique we're going to learn here. Before I erase, any questions on that problem? So if n is less than d, And D can be written as a product of factors. We're going to decompose the fraction into the sum of partial fractions. So this is the kind of the next technique that we're learning here, called partial fractions. Partial fractions, there's two conditions. Two conditions for partial fractions. The degree of the numerator is less than the degree of the denominator, and D can be written as a product of factors. You got to have both those things have to be true, and then you can apply this partial fractions technique. So let's just check this one. Do I have both of those conditions met for this one? First of all, is the degree of the numerator less than the degree of the denominator? Yes. Degree of the numerator is 1. Degree of the denominator is 2. Right? The power. We're looking at the highest power of x. 1 and 2. So that's got that. Can we rewrite that as the product of factors? In other words, does it factor? Does it factor? Remember this from back in the day? Doing this? So we try, right? 2x and x, and then what are we saying? We're saying we need to multiply to -1 and add to -1 also. Can we do it? +1 here and -1 here. Does it work? Multiply to -1 and then add. So we got +1 and -2 adds to -1. So also check. So now what we want to see this is, we want to see this as the result of adding fractions together. In fact, we want to see this as the result of adding fractions with denominators 2x plus 1 and x minus 1. Because when you add two fractions like that, what do you have to do? What do you need in order to add two fractions together like that? Common denominator. What would the common denominator be? Times, right? So there it is, right? So if we were to add these two together, we would get something that looked like that, right? Because we got the right common denominator. So the question is, what values of a and b do we need so that when we add those two together, we would actually get the rate function that we started with there, with 5x plus 1 in the numerator. Okay, so how do we add these together? So we know our common denominators can be 2x plus 1 times x minus 1. So to the first fraction, what do we have to do? We got to do that. And the second one? We're going to multiply top and bottom by 2x plus 1. And now we have the common denominator, and now we can add. So just as a preview here, so this whole thing right here, that has to equal what? 5x plus 1, right? So we got to get the a times x minus 1 plus b times 2x plus 1. If we can get a and b such that it equals 5x plus 1, then we've got it. And then we have a rate function that we can do it separately. We can do these two terms separately. So that's kind of a preview of where we'll start on Friday.